Hi folks, and welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to use differentials to estimate errors for small changes. What we're going to do is we're going to look at number 46, section 3.9 if you're in my current calculus text. And the idea here, if you read the question, it says there's a 0.5% error in the measurement of the length of the side of a cube. So I started this by drawing a cube, and then I called this length x, x, and x. These would all be the same because it says cube. The tough part about some of these problems is unraveling the language here. So this 0.5% error in the length, right? So when you calculate a percentage, let's say I've got some thing, I'm just going to call it like z, whatever that is, and I'm calculating a percent change. I would do that by taking the change in z, whatever that is, and then dividing by z. So for example, let's say I start with the number 10, and then we change by 2. So the delta z, let's say, is 2. Then the percent change we would get by taking 2 over 10, multiplying it by 100. All right, to make it a percentage, so that would be a 20% change. So in this example, the 0.5% is referring to a percent error in x, this measured length. The error in x, the percent error, would be change in x over x. Now, if I take some sort of change in x over x, that's going to give me a decimal. If the percentage is 0.5, then the decimal would be 0.005. So in other words, in this problem, delta x over x must be 0.005. And again, notice to take this and make it a percentage, you would multiply it by 100, which would put the decimal there. That's what this is. Now, we're looking for changes in volume. So I'm going to start by volume equals x cubed. I'm going to calculate dv dx. Right, that's going to equal 3x squared. Now the reason for doing that is because I'm interested in a change in v, and that's what that dv is. It's a differential of v. I'm going to go ahead now and bring this up here. If I can solve this for dv by multiplying by dx, so this is going to read dv equals 3x squared times dx. Now if I had a value for x and a dx, I can now just calculate a dv, but in this problem we don't. We have percent differences. And remember what we're looking for. The question actually asks for the percent error in the volume and surface area. Right now we're doing the volume. The percent error in the volume is equal to the change in volume over the original volume. And what I'm going to do is approximate that by using dv over v, where dv and delta v are approximately the same for small changes in x. So in other words, if I want this to be a percent, I need to divide it by the volume, both sides. dv over v now basically is the percent change in volume. Except it wouldn't be a percent, it would be the decimal change in volume, which is basically what we're looking for. Now on the right-hand side, I'm going to go ahead and just take the volume and write it x cubed, because that's what the volume's equal to. And this is now equal to 3 dx over x, because we have x squared in the top, x cubed in the bottom. Now, dx over x is the value we know. Changes in x and dx are the same thing. So this 0.005 is equal to dx over x. So we actually have this value here. So this is going to be 3 times 0.005. And what we get here is 0.015 out of that. So this is our change in volume now as a decimal, or as a percentage. That would be, we would multiply it by 100, that'd be 1.5%. So our percent error in volume, 1.5%. Got that one done. All right, I'm going to take a moment now and get rid of this work, and we'll talk about how to handle the surface area. I guess I don't need this anymore either. Okay. Surface area now. So the surface area of a single face here is x squared, and there's 6 of them. So I can either write that x squared plus 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 x squared, or I can just multiply that by 6x squared, which I think I'll go ahead and do. Similar to the last problem, I'm now going to go ahead and calculate dA dx. That's going to equal 12x. This again is separable, so dA can be written 12x dx. Now again, what we're looking for is the percent error in the surface area. So I'm going to divide this by A, because change in A over A is going to give me the decimal change, like decimal percent change. I would have to multiply it by 100 before I can actually call it a percent, but that would give me the decimal first. And over on the right hand side, I'm just going to take note that the area is equal to 6x squared. Now 12 over 6 is 2. X over x squared is going to give me a 1 over x in the bottom. Now dx over x, where'd it go? I guess I erased it, but that was coming from here. Dx over x is 0.005. And again, this is 0.5%, right? As a decimal, to turn this decimal into a percent, you would multiply it by 100. That'd be 0.5%. So this value right here is 0.005. So this is going to be 2 times 0.005, and that's going to be 0.01. Now, to make this a percentage, we would multiply it by 100. Therefore, the percent error in area is 1%. So a 0.5% error in the measurement of x is going to give us a 1% error in the area and a 1.5%, or at least up to a 1.5% error in the volume. Now you might wonder a little bit about, well, why are these not the same? Well, here's why. Look at the area calculation. The area has an x squared. So this error here effectively is being multiplied. It's, if I think of this as 6x times x, there's error in this x and this x. When you do the volume calculation, 4/3 pi r cubed, I'm sorry, sphere. Let's see, x cubed. All right, that's x times x times x. The more time the error is used, the larger the resulting error is in the calculation. So there's error in this x, error in this x, error in this x. So the error in that x is being multiplied 3 times, whereas in the area calculation it's only multiplied once. So that's why we have a larger potential error in the volume against the surface area. So anyway, I hope this video helps demonstrate how to use differentials to estimate error. Have a great day.